Rio Grande do Norte. He did his PhD and his first postdoc at Unicamp, working with molecular dynamics in the group of Douglas Galvão. Then he did, after a postdoc at Unicamp, he did a postdoc at Rice. He came back to Universidade Federal do Rio Grande do Norte for a postdoc, and now he's a professor there. And today he's going to talk to us about mechanical control of adhesion and motion at the nanoscale. So thank you very much for accepting the invitation, and you can start as you please.
Thank you for the invitation. As mentioned, my name is Leonardo, and I'm going to present this work here. And the presentation has two parts. The first one, I'm going to talk about controlling adhesion in this material, COF1, using strain. And later, I'm going to talk about controlling motion using mechanical that we carried out. I'm going to talk a bit about the context of the research, some literature work, and what's the idea of why people are working with this kind of subject. So I'm going to be talking about some context and some results here about our work from 2019, and also here some context of this work here, and some results that are going to be published pretty soon. And then I'll finish the presentation. So first part, that is controlling adhesion in COF1 using strain. So these are the presentations about mechanical properties today, but it's a bit different than what's usually done, because usually when you are talking about mechanical properties, we are talking about stretching the material, calculating Young modulus, and seeing if the material is brittle, ductile, getting the focus of the presentation today. What we are going to be talking about mostly is controlling other properties using mechanical stimulus. So, for example, I think a very common case is piezoelectrics. In this case here, you're deforming the material, and then the material, you get charges appearing in the material. So if you put a voltmeter in the edges of the material, you get some voltage, because of deformation and either a compression or you're either stretching the material or compressing the material, and then you get some charges appearing, so you can get that reading with the voltmeter. So this is the first, I think, the most common case that people are familiar of controlling properties using strain, but there are many others that I'm going to talk about today. And there's also the opposite, but I'm not going to be talking much about the opposite. Apply a voltage and we get a deformation. We are mostly interested in this case here, where we apply the mechanical deformation and we get some change in other property as a result. And this is another example of that you can find in the 3D scale for 3D materials. And you have here a material that you can control color and transparency applying strain. So that's another possibility. And this is a polymer. So for a polymer, you can get large effects because the polymer withstands larger amount of strains. But many other materials, for example, I have here some other 3D materials, for example, graphite, diamond, silicon, and those two here are piezoelectric materials. And you can see that with a small amount of strains, you can already break the material. When you go to the 2D world, to 3D materials, it's quite different, because to the form of carbon, you get a very large amount of strain before it breaks, and also for silicene, phosphorine, and other materials made of phosphorus. And these two here, they are piezoelectrics that are 2D materials. So you can see that for piezoelectrics as well, they withstand large amount of strain. And why is this interesting? Why is this important? The reason is that, for example, in piezoelectrics, the more deformation you can apply, the more charge you can get in the material. The charge depends on the amount of strain that you apply. So since in this kind of material, you can apply large deformation before seeing any kind of fracture, you can see large effects happening in this kind of materials. So let me give an example of the kind of things that people are researching. But before that, I'll talk a bit about how to apply strain to the material. Three common ways that you can think about it. In this case here that we call uniaxial strain, we are applying strain in just one direction. It could be this direction or the other direction here. In this one here that's called biaxial, you're applying in both directions, in the y direction and in the x direction. Some 2D materials, they are like fullerene, they have some buckling. They're not completely planar materials. They are 2D materials, but they are outside of the plane. And in this case, you can either stretch or compress in this vertical direction. So I'll talk a bit about this material later, this fullerene. I'll talk a bit first before about MEOS2. And you can see here that for this material that is shown here in A, you really can control the electronic properties by a large factor by applying strain. So for example, without strain, you have a material that's a semiconductor with band gap around 1.8 electron volts. When you apply strain, it can go, if you compress the material using biaxial strain, if you compress the material decreases the gap, and the gap becomes indirect. If you stretch the material, if you apply tension to the material, you have even more a change in the band gap. The material becomes first an indirect band gap semiconductor, and eventually it becomes a metallic material. So we really can control by a large factor the gap of the material by applying mechanical deformation. And this kind of effect can occur because you can apply large amount of strain to the material without causing a fracture in MEOS2. Just to show that this is not really a particular effect of MEOS2, I have results here for fullerene. And you can see here that I'll discuss more this result here that's obtained with GW. That's usually quite accurate for calculating band gaps. And you can see here that for fullerene, the band gap usually is around 2.3 electron volts. And by stretching the material, you can increase the band gap. And by compressing the material, you can decrease the band gap. And these other calculations here, they're not with GW, so the band gap is a bit underestimated. But you can see that you can also control the band gap by applying uniaxial strain or by applying vertical strain. Here you can see that the material becomes a conductor if you compress along the Z direction. So this is about electronic properties, but also the electric properties change a lot by applying strain. So I have some results here from this work, and you can see here that's about thermal conductivity. And they apply a small amount of strain for silicon and diamond nanowires and thin films, and you can see that there is a large variation in thermal conductivity for both materials. So you can also control electric properties by applying strain to the material. And this is getting more close to what we actually did in our paper. And here we have MEOS2, where they created a pore in the material, and then they apply strain. And as you can imagine, since you're applying biaxial strain, you're pulling in this direction as well. This pore will increase as you apply deformation. So if you apply enough deformation, you can get water to flow through the material, and this can work as a molecular sieve. The water will flow, but it's not large enough to allow the diffusion of the ions that are in this liquid here, in this salt water. One thing that's a bit difficult about this work is that you have to create a pore that's of specific size in a material. So something that might be more practical is using a material that has already pores, like you can see here. This is a material that's formed of carbon and nitrogen. And then by applying biaxial strain, you can increase the pore size. So in black here, you can see the pore diameter. And as you apply strain, biaxial strain, you're increasing the size of the pore. And eventually you can allow water to flow. And you can also control the flow of the water by applying the amount of strain that you want to the material. And once again, the water that passes through the pores, they are pure water. The ions cannot pass through these pores, so you can also use this kind of configuration to purify the water, to remove the salt from the water. So what we were trying to do here is trying to see if we can also control adhesion. So to control the flow of water, we want to see if we control adhesion by applying strain. And also to what degree this can be done, and for what end can you use this kind of effect. So this work was published in 2019 in Carbon, and this is the name of the work. We also wrote a small feature for our website that is less technical. It's more, it's easier to understand, and it's more about discussing the results without discussing much the methodology of what we did. So let's talk a bit about the material that we are investigating. So we were investigating this material here, Covalent Organic Framework number 1. This material has been synthesized in 2005. This work here just synthesized many COFs, many COFs, and this is one of those that were synthesized in the initial paper. There are some investigation in its properties, theoretical investigations. That one that's interesting is this paper here. So if you want to read a bit about the electronic properties of the material, for example, you can find some results in this paper here. This material is composed of carbon, boron, hydrogen, and oxygen. And it has those large pores here. Let me talk a bit about. We used both classical simulations using ReaxFF and DFT simulations. This is the method we use for the ReaxFF simulations. We used lamps, and this is what we use for the DFT simulation. Importantly, we used a function node that has van der Waals correction. So if you want to talk adhesion, we have to first define it. So we have here, we are using graphene to measure the adhesion with coffee 1. So what we were doing is we first put graphene very far from the COF1, so we don't get any interaction between the two materials. And then we measure the energy of this reference state. And then we wanted to measure the interaction between these two materials. So to do that, to measure that interaction, we move graphene closer to the COF1. And then I'll talk a bit about more how we can get the equilibrium state. I will discuss a bit more later how to do that. But we move this guy close to the surface and we measure the equilibrium state. And then we get the equilibrium energy of the system. By subtracting one from the other, we are basically separating the interaction energy in this kind of calculation. And then we divide by the contact area between graphene and COF1 to get the adhesion material between COF1 and graphene. So let's talk a bit about why we expect to have a change in adhesion when we apply strain to this material. We are working here with uniaxial strain, and we apply strain in this direction here. So you can see here what we are doing with this movie. So we are deforming the material in this direction. So first we optimize the structure with DFT. This initial calculation is with DFT. And then we optimize the structure. We apply some strain, 0.5%, and then we optimize the structure. And then we increase a bit more the strain, optimize again, and repeat this process over and over. And then you can see this is the result that we get from this process. And you can see here that something changed at some point in the simulation. And you can see what happened more clearly when you look at this. If we increase the strain above a certain value, what we see is that the material that initially is in the plane, it moves outside of the plane. And why this occurs, you can see at the beginning, like this region here, where we have this hydrogen and this oxygen here, initially those atoms are far apart. But you can see here, as you start increasing the strain, these atoms will move closer to the oxygen, and this region here becomes very dense with atoms. So eventually some atoms will move out of the plane to decrease this density that starts causing repulsion in this region here. For example, in the final configuration that we have here, I think it's pretty clear to see that if we try to rotate this ring here back to the plane, you get a large amount of repulsion because you have this carbon here and this carbon and these hydrogens here and this oxygen close together in a very small region. So to reduce this kind of repulsion, these phenyl rings here, they can rotate outside of the plane. And when the strain is large enough, we get this kind of effect. So our idea was, graphene is a very planar material. So if we put graphene on top of COF1 here, we should get a good contact area because both materials are very planar and they should have good contact area. When we have this kind of rotation, this material is not very planar anymore. And if we put graphene on top of this structure here, we expect to see less contact area. The interaction should be a bit smaller because graphene will be farther apart, for example, from this ring of atoms here. So that was the idea, but we have to do the calculation to see that this actually occurs. But there are some issues in order to do this calculation. We need to have a graphene that's quite large. Why that? Because if we have a small piece of graphene that we put here, where we put the piece of graphene will matter. If we put it here in this pore, you have very little interaction. If we put it here, it will have more interaction. And depending where you put the graphene, you get different results. We don't want this kind of effect. We want to get an average of the interaction. So in the end, we use something that's like this, a quite large amount of COF1 and graphene, so we can sample both the pore region and the region that has atoms. And okay, and in addition to that, we have to have a supercell that's a bit large, because once we put graphene here, this is a unit cell, and we are going to replicate the unit cell. If we put a graphene that is small here, we between this graphene and graphene that's on the other unit cell. We don't want that because we want to basically get an interaction between COF1 and graphene. We don't want to get interaction between graphene and graphene. So we don't want this kind of effect. So we need to have a COF1 that's a bit larger than the graphene that we are using. So in the end, and there's another constraint that I want to talk about, is that we have to allow graphene to evolve in time and also to optimize its configuration. The reason for that is that if we put graphene on top of COF1, what might happen is that graphene might deform and follow the shape of the material. So maybe when you allow graphene to evolve in time to optimize its configuration, maybe it will deform, and maybe you also assume a non-planar configuration, and maybe the energy will be large still when you have strain. So we want to make sure that we're missing this kind of effect. In the end, the problem that we have here is that because of those three constraints, we have a simulation that is quite large, and it will take many steps of calculation. So to do this kind of calculation with DFT is not feasible. So we will think about calculating the adhesion using a classical potential React FF. So to check that we get a good description of the material with React FF, we optimize the material within the classical potential. And you can see here that we got good results. You can see here that the unit cell is a bit smaller in React FF, both in this direction and this direction here. But overall, we have a good agreement between DFT and React FF if we're just talking about optimization, just energy minimization. But since we are going to evolve in time, because we really want to give the opportunity to graphene to deform to follow the surface of COF1, we allow the system to evolve in time within a molecular dynamic simulation. And what we see is that when we allow temperature, there is not a good agreement between DFT and React FF. You can see this kind of ring rotation here that happens in React FF. So that will for sure change the values that we get for the energy. So we have to be careful to avoid this kind of ring rotation. So in the end, our methodology was the following. We optimize the COF1 using DFT, and then we replicate the unit cell to obtain a large sheet of COF1. And after that, we fix the position of the COF1 atoms with the idea of preventing ring rotation. We graphene to the material, like is done here, and then we go through this process. What we want to do here is to get as close as possible to the minimum, to the global minimum of the energy of the system, to calculate the adhesion accurately in a precise manner. So we ran 5 cycles of optimization and then thermalization at 1 Kelvin. So we minimize dynamics to allow the system to move around and try to find a better position, and then we minimize the energy again. And we repeat this process 5 times to try to get as close as possible to the minimum energy of the system, to the global minimum energy of the system. We tried different temperatures as well, and I'm showing the results for 1 Kelvin. For example, I tried 10 Kelvin, 200 Kelvin. I'm showing 1 Kelvin here because this is the temperature that we use in this process and energy possible. So I'm discussing the results that got the closest to the global minimum of the energy. And one last thing that's important to note that I'm not going to discuss here is that we also took some care to verify that, for example, when we are using this kind of frozen structure with HexFF, is the interaction between COF1 and graphene similar to what we would get with DFT? So we did some tests to make sure that this is at least a good approximation. I'm not discussing this now, but I put some slides in the end of the presentation. So if anybody is curious about how we managed to estimate that this interaction between COF1 and graphene, as long as the COF1 is frozen, it's at least good enough, I can talk a bit about that in the end of the presentation. But going for the results now, like I mentioned, I calculated this energy here. I moved this guy close to the COF1, and then I run this process here to get result that's very close to the minimum energy of the system, and then I get the equilibrium energy, and then I calculate the adhesion, and you can see the results here. Each point here that I show in this graph corresponds to a simulation like that. For example, for this point here, I have a COF has strain that's relaxed, and then I move graphene. I calculate the energy of graphene far and close, get the adhesion, and this is 1 point. And then I apply some strain to COF1, and then optimize COF1, and then I put graphene on top, get this reference energy, get the equilibrium energy, calculate the adhesion, and this is another point. So for each value of strain that I'm applying, the adhesion, and I get 1 point. And you can see here, as I repeated this process for higher strain values, you can see that as we expected in the beginning, when the material moves out of the plane, we have a large decrease in the adhesion by about 30%, the decrease that we get when we have this kind of ring rotation out of the plane. So we really get a decent amount of adhesion. Just another side note, we also calculated the mechanical properties of this material, COF1. We got the Young modulus, we got the ultimate strength, we got ultimate strain. But it's a bit outside of the scope of this presentation, so I'm not going to discuss these mechanical results here today. But you can find them in the paper that I mentioned that is on carbon. Let me talk a bit about how we could possibly use this kind of effect. So we have here what we call nanotweezer. And the idea is similar to what we have in a tweezer in the macro scale. So basically, if you want to pick something that's very small, you get a tweezer, and then you press the tweezer to pick up the object, and then you can move it around. And when you want to drop the object, you release the compressor to apply to the tweezer to release the material, and then you can move it around using the tweezer. But it's not easy to do that kind of movement, accomplish this movement in Nanoscale, because the structure is far too small for you to pick up with big objects. So it's pretty difficult to transfer materials in the nanoscale. If you look at some papers, for example, they put some mask and they grow some materials and then they transfer the mask. It can be challenging to transfer materials in nanoscale.
Leonardo, I'm sorry. I'm not
Yes.
sure if you are showing something already or not yet.
No, not yet. I'm just discussing
Okay,
generally.
okay.
I'm
Yeah,
looking for the
I
view
will.
soon.
Okay,
Sorry.
okay. No, no problem, no problem.
And then you can see here what we are trying to do here. Sorry, I was talking a bit about the macro scale, and this is the analogous in the nanoscale. So this calculation, we are going to show that we are going to apply and remove strain to COF1 during the dynamic simulation. So we cannot freeze in this simulation here. So we are actually going to see this kind of ring rotation that I mentioned before. For this effect, it's not really important if this ring rotation occurs. All that we need to see this effect that I'm going to be talking about is that we have two configurations. One where we have a high adhesion, one with low adhesion, and you have to be able to change these configurations by applying strain. So in the case of this classical calculation, the configuration that has higher adhesion is this one with the strain. So for the classical calculation, high strain that we have here corresponds to high adhesion. And the relaxed structure has low adhesion. And we put a graphene here. So we are going to move this structure below to see what happens. Here, we see that the graphene stays with the upper COF1, right? So what we are going to do next is we are going to relax. We are going to relax this COF1. We are going to strain this COF1. So now this layer will have high adhesion with graphene, and this will have low adhesion with graphene. And then I'm going to do that. I'm going to change the configuration in the simulation. And then you can see that now this has high adhesion, this has low adhesion. And then I'm going to repeat the process. Now I'm going to move this structure down. And since adhesion is high with the bottom layer, it will transfer the structure. So the idea of this nanotweezer is if you want to pick up something, you increase the adhesion. In the case of the classical, you apply strain, increase adhesion, you pick it up what you want to pick up. And then after you pick it up, you release the strain, you decrease the adhesion, and then you can transfer it to another substrate. That would be the idea. It's a proof of concept. I'm not sure how, if that could be actually done in experiments, but I'm going to discuss a bit, at least if you can apply deformation to a 2D material in a laboratory. And the answer is yes. There are many ways to apply strain to a 2D material. I'm going to discuss some here. So for example, if we have a material that has some thickness, like this one here, if you bend this material, the upper part will be tension and the bottom part will be compressed. So if you put a 2D material on top of this other elastic material, you can see that it will become tension. So you can apply tension in this manner. Maybe a more straightforward way would be to put the 2D material on top of elastic substrate, and then you pull the elastic substrate. And as the substrate is elongated, so will the 2D material. These two manners here, they apply uniaxial strain. That's what we need for our proposal. But you can also apply biaxial strain. For example, here we have a material that has high thermal expansion, PDMS, and you have, in this example here, MeOS2 that has lower thermal expansion. And as you heat this polymer, stretch, it will apply some strain to the MeOS2 that's on top of this polymer. You can also make this kind of apply this kind of deformation by using a piezoelectric material. And you can see here some results from experiments. And you can see that you can actually apply strain to the material in the lab, but the problem is that the maximum strain that they get nowadays is around 4%. And to get the effect that we predict should happen in COF1, we need much larger amount of strain. We need around 15% strain. So it might, nowadays I'm not sure if it's possible to actually produce this kind of effect because the method that they have to apply strain to the materials only produce a small amount of strength. So we need a new method to apply larger strengths in order to be able to see this proposal happening in a lab. The first part of the presentation that talks about this control of adhesion with strain, and I move into the second part that's controlling motion using mechanical cues. Let me talk a bit about moving objects at nanoscale. This can be quite a challenge to move objects at nanoscale, but nowadays there is good control of movement at nanoscale. So I have an example here that you can find in this link here. These researchers, they made a video. You have a boy that's playing with a ball. In the case, the ball is a CO molecule, and also the boy is made of CO molecules. In total, they have 65 CO molecules. And they make a video of this kid here throwing the ball up and playing with the ball, and it's quite interesting. And they really show how good is the control of movement at nanoscale nowadays. But the problem is, you have good control, but it's difficult to achieve that. In here, in order to make this video that I'm not showing, they needed 242 images to put together and to animate the video. And to make these images, they needed 4 researchers. They are very specialized, very good at what they are doing, and they need to work at 2 weeks, long hours, days to produce this video. So it's possible to control movement, but it's not easy at all. And what they did here was using a microscope to move the atoms, or the molecules, to where they needed to be. You can use an AFM, you can use an STM, but one thing that you also have to consider is that the efficiency of this process is very low, because the work that you are doing is very small, because this structure is an atom or a molecule, and you're dislocating this structure here for nanometers of distance. So the work that you are accomplishing is very low, but the energy that you have as input is enormous, because you have a microscope and you need to operate the microscope, you need to create the vacuum. So if you think about the efficiency, this is not efficient at all. This is very poor efficiency. So it would be nicer to have another method of moving objects where we have better efficiency, and we also have an easier method to move the object. An inspiration to try to achieve that you can find in biostructures. So for example, here we have a blood vessel. And in biostructures, in organisms, for example, this happens all the time, right? You have always cells and nutrients that are moving inside our blood vessels, and they are getting to where they need to get by themselves. You don't need to have somebody that's outside your body moving the cells around for them to get where they need to get. So that would be the ideal, if the objects move where they need to be by themselves without needing the external manipulation. So how is this accomplished in a biological system? One way that is accomplished is this one here that they call durotaxis. And for example, let's say a person has a cardiovascular accident, and as a result of that, you have the formation of scar tissue. And this scar tissue is more stiff than the normal tissue of the blood vessel. And naturally, by themselves, the cells will move towards regions that are stiffer. So when this accident happens, this region will become more stiff, and this stiffness will attract cells to this region here, where they will hopefully be able to repair what happened in this region here. So this durotaxis is the movement of cells towards regions that have higher stiffness. And I like this example here. It really illustrates well this kind of effect. So these researchers here, they made this substrate here, and this square region is more rigid, and this is more soft. And they put cells on top of this configuration here, and you can see that over time they start concentrating in the rigid region, and if you give enough time, almost all cells go to the rigid region. So they really tend to move towards high stiffness regions. So this is the biological case. And can this be accomplished in nanoscale? The answer is yes. This is unfortunately not the work of Sheng and co-authors that was published in Physical Review Letters in 2015. And to accomplish this gradient of stiffness, what they did was to couple those coils to graphene. Below here, you have a graphene substrate. On top, you have a graphene nanoribbon. And then you couple the graphene that's on the substrate to some coils. The coils here will be softer, here will be harder. Allow the system to evolve in a molecular dynamic simulation. And you can see some snapshots here. Naturally, this nanoribbon will move towards the hard region of the substrate. So they see this kind of effect happening in nanoscale as well. Why this happens? I think this graph, it really helps see what's going on here. So they are plotting, this is the stiffness in the X, and in the Y they have in purple the interlayer potential. Here they have interlayer potential, and here they have the atomic fluctuations. So when you have stiffer coils, this substrate here will have lesser atomic fluctuations, right? When you increase stiffness, the fluctuations decreases. And when this guy here oscillates less, the average energy will increase with the ribbon that's on top of it. So as you decrease the fluctuation, the energy becomes more negative. The interaction becomes more attractive. So that's what is happening here in what they call nanodurotaxis. And once again, what's interesting here is that we don't have an external manipulation to move the object. The object will move itself to where it needs to be. So we want to see if we can also produce this effect by a different method. And we managed to do that in what we call the nanomechanotaxis. And this is the configuration that we are simulations. I'll talk a bit about pretty soon. This work is under review nowadays. Hopefully it will be published soon, but it's already on archives. So if you want to see some details of what we did here, there are results that I'm not including in this presentation as well. And you can see those results and the discussion of these results in more detail in this paper here that's nowadays only on archives. Hopefully it will be published soon. And these are the authors of this publication. These are the methods you are using here. I'm using the charm potential. This is a non-reactive potential. It cannot describe the formation or the destruction of bonds. But in this case here, we don't expect to see any kind of effect like that. We don't expect bonds creation or destruction of bonds. So for what we need, this potential is and the good thing about the charm potential is that it's very inexpensive in a computational point of view. Some structures that we are simulating are quite large. I think the largest simulation that we used had around 100,000 atoms. So it's easier to run the simulations by using the charm potential. We don't have to wait forever for the simulation to end, especially since the amount of time we're simulating is simulation using the LAMPS MD package. We use the NV ensemble, so it's important to realize that the energy will be constant through these simulations, and we use a time step of 1 femtosecond. We did simulation with CNTs and with nanoribbons. And in the case of the CNTs, we used a zigzag nanotube, and the spiral substrate is armature. In the case of the nanoribbon, the moving ribbon, it can be both zigzag or armature. This is important. We will discuss a bit later what is the effect of the kind of ribbon that we use. And the substrate will always be armature graphene nanoribbon substrate. So let's begin with the nanotubes. So this is the initial configuration. And once I play this video here, you will see this tube here moving. The initial movement is driven by van der Waals interactions. Why? Initially, this tube here, it's partially outside of the spiral substrate. So the van der Waals energy is not very low. If this guy here moves inside, the contact area between the tube and the substrate will increase, van der Waals energy will decrease. And you can see that in the video. So as I hit play, it will move inside to decrease its van der Waals energy, it moves inside, and eventually it will stop inside. And then it will move outside. Eventually it will move completely outside of the nanotube and move back again. And as you can see, friction is pretty low in this simulation, so we actually managed to not only make this structure move, but we also get an oscillator as a result of this configuration here. So what is happening here? I think this kind of energy graph is very useful to see what's happening. So you can see here these arrows, A, B, C, D, E. Each one corresponds to one configuration. So this energy here is of configuration A, this energy here is of configuration B, and so on until this final configuration here that's associated with this final energy here that's associated with configuration E. It goes on because there are many cycles of the oscillation. So at the beginning, like I mentioned, you can see here, we also defined the energy, the zero of the energy as for van der Waals inelastic energy as the initial energy. So the initial energy is zero for elastic and van der Waals energy. So as this nanotube here moves inside, it will decrease its van der Waals energy. And since the energy is constant in our simulation, this energy will have to, some energy will have to increase as a result. Part of this increase is an increase in elastic energy. And why this elastic energy is increasing? It increases because when the tube moves inside the spiral, it will become bent. A ruler, when you bend the ruler, you can see that the ruler wants to go back to the initial configuration. When you bend an elastic material, it will have some elastic energy in the configuration. So when you bend a ruler and you release the ruler, you can see that one edge starts moving to release this elastic energy. So that's what's happening here. As it's moving inside the spiral, as the spiral is curved, it's not planar, it's not straight, it's curved. As it moves to the curved region, it will start increasing its elastic energy. And when it moves inside, it becomes initially curved, and it will increase a bit the elastic energy. The rest of the energy becomes kinetic energy. So this initial van der Waals energy becomes a bit of elastic energy and mostly kinetic energy. As it moves inside the spiral, the elastic energy increases. You can see here, and this increase is associated with a decrease in the kinetic energy. You can also see here that as long as the tube is completely inside the spiral substrate, the van der Waals energy will remain constant. So it will only change when it gets outside here. I'll talk a bit about that later. So it's moving inside this spiral, the kinetic energy is decreasing, the elastic energy is increasing. Eventually, all kinetic energy becomes elastic energy when it stops here, and then the motion reverses. In order to decrease the elastic energy, it will move outside, and you can see here that the elastic energy is decreasing and the kinetic energy is increasing. Eventually, it will reach the end of the spiral, it will leave the spiral, and as it leaves the spiral, the contact area between the mover and the substrate will decrease. And then you have a spike in decrease in the kinetic energy. It stops again and reverses, and this motion continues. One thing that's important to note here is that motion is not only driven by elastic energy, it's also driven by van der Waals energy. To see one case where the van der Waals energy does not play a part, we created this other configuration here. Since throughout the simulation that never leaves the spiral, you can see that in the simulation the van der Waals energy is constant, and the elastic energy is always, the movement is completely driven by elastic energy. The van der Waals energy plays no part at all in this simulation here. So it begins here at this region that has high elastic energy. Once again, I define the initial elastic energy as 0. So it will eventually decrease. As it decreases, it will become kinetic energy, and it will start moving faster. When it reaches this region here that is straight, this straight region here that connects the two spirals, the kinetic energy will be maximum because the nanotube is straight. So the elastic energy is minimum in this straight region here. Eventually, it will go inside this other spiral, and then it will increase the elastic energy until it stops and reverses, and this process continues. So to understand what's happening in the simulation, I think this formula can be very useful. This formula here, it will give the elastic energy per unit length to bend a thin rod. This is a good approximation for a nanotube. We did some tests to see if this approximation was good for a nanotube, and it is good for a nanotube. So you can think about the elastic energy of the nanotube using this formula here. Y here is the Young modulus, I is the area moment of inertia, and kappa is the curvature. If you have a circle circumference, the inverse of the radius is the curvature. For a circle, the curvature is constant, and it's the inverse of the radius. So this is the curvature. And what you see here is if you have this curvature changing, if you have a gradient of curvature, and if you calculate the gradient of this curvature here, and I'm assuming that this constant here only values along a single direction, along a coordinate q. And if you assume that, you can see that you have a force that will be given by this expression here. So basically, as long as you have a picture, you have this variation here, you should have an elastic force that will either try to stop the motion if the curvature is increasing, or will drive the motion if curvature is decreasing. And one way to achieve this gradient of curvature is by using a spiral. In this case here, we have an Archimedean spiral. This is the theta. This theta here is this angle starting. Theta is 0. As you go outwards in this spiral, as you move outwards in the spiral, this theta value will increase. And dy here is the curvature, is kappa. So as you move for example, the nanotube inside, the curvature will be increasing, and then with this gradient of curvature, you will have a force. So this elastic force will resist this tube that's trying to move inside the spiral, eventually stopping the nanotube and driving the motion in reverse. So that's basically the basic physics of what's happening in our oscillator. So the question is this a specific effect for nanotubes, or you can see that happening in other materials? To investigate that, we used simulations with graphene nanoribbons. It's the same setup. We start with the ribbon with a bit outside, so the van der Waals energy will move this guy inside. It will keep moving towards the center. Eventually, it will stop, and the motion will reverse, because in this region here, you have high elastic energy. So you can also see this effect with nanoribbons, and in principle, with any material that you are increasing the elastic energy as it moves inside, you should also see this effect. Let me talk a bit about the configuration. So I mentioned before that if I'm using a ribbon that's armature or zigzag, they should have an effect. So in both simulations here, the substrate is armature. In this case here, this guy is also armature, so both are armature. And in this case here, this one is zigzag and the substrate is armature. And as I allow it to move, you can see that very quickly, this guy here will stop moving. And this guy here is slow and steady. It keeps moving inside, and it keeps moving inside, and it's not stopping. It will move inside until it stops and reverses the movement. In this case here, very quickly, the the kinetic energy, it was essentially dissipated. It's not really moving in any particular direction. It's just oscillating. You can think about the energy that you have initially. It became essentially internal atomic motion. And you can see here how the energy changes in both cases. This is the energy for the case where you have the this configuration here, the incommensurate configuration, and you can see that the energy it remains mostly constant. And when it gets very close to the spiral, to the center of the spiral, this is close to the center of the spiral, the kinetic energy will decrease, elastic energy will increase, and the motion will reverse. So here it's approaching the center of the spiral, here it's moving away from the center of the spiral. When you have this kind of configuration here that's commensurate, you see that very quickly this kinetic energy, initial kinetic energy, it becomes disordered. Like you don't have any kind of order changing kinetic energy. Thermal motion, basically, in the case of the commensurate case. So what is happening in this simulation here? What's the reason for this difference between the two cases that we considered? And the explanation for that is that this case here, you have super lubricity. Let me talk a bit about that. You have here two pieces of graphene, and here it is in one orientation, and this other here, I have rotated this structure. So I got this structure and I rotate it to get this one here. If I stack two layers that have the same orientation, like if I stack this layer with another that has the same orientation, I will get something like this. This is the stacking that has a minimum energy. This is the AB stacking. And you can also have configurations with higher energy like the AA stacking. To see this more in more detail, I calculated this map here. So here I have a small piece of graphene on top of a larger graphene. And what I am doing is I have this configuration here. I calculated the energy. This is 1 pixel in this image here. So the energy that I get from this interaction between the lower and the top graphene will be 1 pixel here in this image. And then I move this graphene a bit to the right and then get another pixel. And I scan the surface using this small graphene. And I get this map of energy here. You have a configuration of very small energy, that's the AB stacking. And you have configurations with higher energy, that's the AA stacking. So what's the problem here? As we're trying to move this, the upper ribbon on this direction here, for example, you are going to leave the low energy configuration and you have to pass through a higher energy configuration before you get to another lower energy configuration. So the problem is that you have if you have a gradient of energy, you have a force. So you have a force that will be preventing this motion from this point here to this point here. So in this configuration, we have high friction. If you first rotate the second layer and then you stack both, you get this kind of arrangement here. So if you try to move the upper layer, in this case, you can see that some atoms will decrease the energy, some will increase the energy. But you won't have any kind of a net increase or decrease of the energy as you see in this case here. And you can see here in the map, this is the map for this configuration here. It's important to look at the scale. This scale, this energy here and here is given in kilocalorie per mole. And you can see that this scale of variation here is much larger than what we have here. It's 100 times larger in this case than in this case here. The variation in this case is on the order of 0.02 kilocalorie per mole, and on the other one is of the order of 1 per mole. So it's much smaller here. So if you try to move the upper structure and the energy is constant, you won't have any gradient of energy, you won't have any force stopping this movement. So you will basically be able to slide the the upper structure above the other structure with very little friction, almost no friction. And this very low friction between the structures is what they call the super lubricity. So one question is, can this kind of effect that we are proposing be realized in a lab, in an experiment? And let's go by parts. This kind of movement of a nanotube inside the other, it can be seen in labs. You have, it's a not very good image because it's an experimental image, and so there are many complications to get a good image. But you can see here they have a small nanotube here that is moving to the side and it's moving back. So yeah, this kind of effect of moving a structure inside moving a tube inside another, they have seen that stuff in nanotubes previously. And they have also seen the super lubricity in experimental works as well. So the super lubricity that I mentioned here, they see that in labs as well. And they also have spiral nanostructures nowadays. For example, here we have a silicon nanowire that has a spiral structure. And here we have some spiral graphene that they cut. It's a kirigami. So they do have spiral structures. So, for example, in this case here, you can think maybe of using this nanowire as a template to grow a spiral graphene structure, for example. And one issue that we have in these kind of configurations is that they are much bigger than what I have in my simulations. So the gradients of curvature will be lower in the experiments compared to the simulations. So they will really need to be careful to try to achieve super lubricity if they want to see this effect. Because if the friction is very, very low, even if the force that is driving the movement is not as high, maybe you can see some movement in this kind of configuration here. So some final remarks to finish the presentation. So like I mentioned, there were two parts of this presentation. In the first one, I talk a bit about controlling adhesion in COF1 using strain. And I talked how 3D materials can withstand large amounts of strain. And this kind of large strain values that you get in 3D materials allows for a good control of the properties of 2D materials. And we show that we can also control the adhesion in COF1. Before, in the literature, there were other works talking about electronic and lattice properties, and we showed another property that you can control with strain in COF1. And we showed how this effect can be used to transfer a piece of graphene between two COF1 substrates. And the second part, we talked about controlling motion using mechanical cues. We talked about how it's difficult to control motion at nanoscale. You have good control, but it's not easy to achieve that control nowadays. And we talked about how it would be convenient if we could use mechanical cues to direct the motion. So use mechanical cues so that the structure can get where it needs to get by itself, without an external manipulator that is driving the motion. And we show that we can use gradients of curvature to drive motion, and we can even drive oscillatory motion using this kind of gradients of curvature. So I thank you all for your attention. I would also like to thank the university that I'm working today to allow me to carry out my research, and also my department that's also very supportful of my research, and also the funding agents of CNPq and CAPS that also allow us to carry out research. So thank you again, and if you have any questions, I would be happy to answer them now.
Thank you, Leonardo. Very, very nice presentation. Thank you. Thank you. We are open for questions now. Does anyone want to ask a question? I have a couple of questions in reality. If you could go back to slide 19. Very, very nice videos, by the way.
Oh, thank you.
Very nice. Slide 19. Is there a preferred direction that these rings are going to move? They all move down, or they all move up, or half of them move down and half of them move up?
I think in this case we saw it moving all in the same direction, but I would guess it is a bit of a coincidence because there
is no broken symmetry.
Yeah, there is no preferential direction, z direction. What I think might happen, for example, if this structure moves down, maybe the other will move down as well, because you have some interaction between this hydrogen and this hydrogen here. Okay. So if one moves down, I think the other should move down as well. But for example,
but the fact that these in different pores, it's gonna move. They could move up. By the way, for example. I am talking about all the substrates, all the material. All of them move up, or all of them move down, or half of them move up and half of them move. Because if there is no broken symmetry, there is no reason for a preferential direction, right?
I agree with that. Like what the simulation would indicate to me is that the direction that one will rotate, the other will also rotate. Why? I'm not sure. Like I know why these two will move in the same direction, but I'm not sure why this one and this direction, because they are too far apart. There's no interaction between this structure and here. I don't know why they should move in the same direction. But what I think could easily happen is, for example, if you pull this structure, maybe it can buckle to the other side. Maybe this guy here will move up, because there is no reason to prefer this structure to move up here or down here. But I would get, once this guy, for example, moves up, actually I think, I think since this guy here is moving down, it would be very difficult, because, for example, if this structure here moves down, if this you rotate in the other direction, and then this you have to move up, right? So it will create some internal strain in the structure. So I think once it starts moving in one direction, all will move in the same direction. But if it moves up or down, it depends on the simulation. But I didn't try to do this many times. So this is what I think should happen, but I don't have the data to back this opinion up.
Okay. I have one more question. That's regarding the nanotube, oscillator. Slide 39. Do you know if they played with the chirality of the nanotubes? Put two nanotubes with the same chirality, or two nanotubes with different chirality, and try to make a rotation movement too, maybe. I don't know.
I didn't try to do this change. What we did here was we chose a different chirality because we were aware of the super lubricity papers before. So we were trying to minimize the friction to make sure that the motion was smooth. So we did this. We chose, I think the outer nanotube is armchair and the inner is zigzag. What I can also say is that there are papers of nanoscallators. They're different. Like what they have in the other papers, they just have this open end here with a tube leaving, and it straight the tube, and it will move outside of another open end. And in this kind of configuration, they also see the effect of chirality. They see that in this kind of configuration, if you have, for example, an armchair tube with an armchair, the inner tube armchair and the outer also armchair, they see that the motion stops more quickly. Yeah, if you really want to maximize the amount of time it's oscillating, it's easier to use different configurations, different chiralities to make sure that you decrease the friction. I think you mentioned rotation. I think there was some paper talking about how the energy dissipated in this kind of oscillator, not for this kind of spiral structure, but for the straight nanotube. And I think somebody mentioned that you get some rotation, but it's been a while since I read this paper, so I'm not 100% sure. But I think somebody talked about that kind of fact. When it starts moving and you have a different chirality, you have some rotation happening in the nanotube that's inside.
Okay. Diane has a question. Go ahead.
Yes. Do you hear me? Yes, I can hear you.
Okay. So thank you, Leonardo, for the presentation.
Thanks for the invitation.
Yes, I have one question is this that George was showing, asking about the spiral. When you have, when you say that the van der Waals contribution is not important, I was wondering what will happen if you add a different nanotube, not carbon nanotube, but a different one. Do you think this is gonna be the same oscillation?
I think there is a work in this direction, not with this kind of oscillator, but for a different oscillator. But for the straight oscillator, I think they did that. I think in that paper in particular, they were saying that the friction was pretty low. If you use, for example, the outside, it's a carbon nanotube, and the inside is a different kind of nanotube. And I think in this paper, they got a very small amount of friction between the inner and the outer nanotube. And I think that, I'm pretty sure that you can also see this motion if you put a different nanotube, because this van der Waals interaction will also happen for different structures. But I think the key issue that you have to consider is if you put a different kind of nanotube inside, if you have bigger or smaller friction. And I think this paper, for some material, they got lower friction, but I'm not sure if this is a general result or if this is a particular combination that will lead to lower friction.
Yeah, but this friction is related to the van der Waals interaction, right?
Yes, yes. But I think because, for example, once the tube moves inside, if you get this kind of very smooth potential energy, so essentially the van der Waals energy is constant. So it's high, but it's constant. So it won't really try to stop the motion. But if you have this kind of bumpy map, like you have many minimums and maximums of energy. So in this case here, you have, if you have a gradient of energy, you have a force. So if you have this kind of a configuration here of energy, interaction between the one tube and the other, then it will likely stop very quickly because the friction will be quite high.
Well, I have two questions. Can I go ahead or someone?
Go ahead.
Okay. Yeah, about the cough that you show when you the tweezer.
Yes.
Yes. Well, I was wondering because you keep the cough rigid, right? When you do this simulation.
In this one, no. I think the edges might be like it might be frozen at the edges because I have to move it up or down. But the most part of the structure is flexible. And that's why you see this kind of spring rotation here, because as long as I'm allowing these structures to evolve, you will see this kind of spring rotation. But you can see very well that it's moving, I think, here. It's like once it releases, you can see that it really oscillates a lot on both the top and the other one.
But then you use the classical the React's first field, right?
Yes.
Just simulate this. Okay. Yeah. Because you show, I think some slide before you show that the DFT predictions is a little bit different of the React's first field prediction. Right?
Yeah, you can get if you make the same calculation for the React's FF, you get the inverse. The adhesion is low at the beginning and high at the end. There is an inverse of the effect. But to see this kind of a tweezer that I mentioned, all that you need is to have a high adhesion and low adhesion configuration. If the high adhesion is with low or high strain, it's not that important for this effect. And the only reason why, if we try to do this calculation with DFT, I don't think it would ever finish. So we had no choice but to use the ReactFF to do this kind of calculation.
So, but anyway, when you did the DFT, you see the opposite effect. But then
for DFT,
just because the DFT, you don't have this rotation very strong, right? That you cannot. Okay, nice.
I think the problem with the classical potential when you have at the beginning, since it rotates, you can see that it has a very large pore here, so it won't have a good interaction with graphene. In the paper, we actually put both results. We put this energy here for the DFT. That's mostly the configuration of DFT. And we also put the results completely with the classical potential. But this is, we believe, is much more accurate because this kind of rotation here, it's due to the potential. We don't see that in the DFT. And we also did some calculation with DFTB as well, and we didn't see this kind of effect as well. So this is particular to the potential. So I think this is a more accurate result for the adhesion. But unfortunately, we cannot freeze the COF atoms if we want to have this kind of pulling the material during the simulation. Because we actually, this is a single input. Once we started the simulation, I didn't do any restarts. So I really want to make a single cut. And in order to do that, I had to allow the COF1 to evolve over time.
Have you tried to use some generic force field like UFF or drying or?
I think UFF would work very well for this material. But what we had a problem at the time is that we didn't have UFF for lamps. I never found any paper describing the application of UFF for lamps. And at least my memory, what I recall from trying to, because since the lamps is very modular, you can think of using the parameters of UFF to create UFF inside lamps. So you can put, like, for example, many torsional terms, but I think there are some parameters for UFF, if I recall correctly, that are not in the paper. So a few parameters they don't give in the paper, so we don't know exactly how we can get those parameters to use the UFF in lamps.
Okay. Last question is, the previous one is the ions selectivity, when you show the water and the ions.
This one?
Yes, this one. This is very interesting. How I'm wondering, how do you, well, first of all, which kind of ion are you simulating? And,
this is not mine, sorry. Like, usually when you see that kind of reference here, it's not my work. So for example, just to make it clear, like what we did was this part here of the COF1 and the other part here of the oscillator, this part here. So this is our work, and this COF1 is our work. But the rest not. But I usually like to give some context of what's going on in the literature to make it easy to understand what's happening. I think at least for me, if I don't give this context, I think it's not very clear what I'm talking about.
Okay. Any more questions, Diane?
No, thank you. That's all. Okay.
Anyone more questions? I have one more. If you could go back to the super lubricity, the simulation of the two armchairs. There is a place where you show the energies.
Yes.
Before there. In this simulation here, the energy is constant in the left side. On the right side, is it constant too?
Yes.
Okay.
So it should be, because the time step, like, usually make some tests to see if the time step we are using, it is keeping the energy constant. Okay. I'm pretty sure I checked the total energy, and it's constant as well. Okay. But it's difficult to see here because it's changing very quickly. So it's difficult to see if at any given time, unless you plot the total energy, if the energy is constant.
But for a real system, you should expect some dissipation, mostly for the right side, right?
Yes.
Would it be possible? Just asking if it would be possible at your level of simulation to include dissipation.
I think I could introduce a thermostat. I think that one of the issues that we get with thermostats sometimes is sometimes it's very, I don't know if the word is aggressive, because when you couple the system with a thermostat, it will couple to every single atom. So I don't really like that method. For example, there are simulations that, for example, we are having a structure that's moving with some speed, and basically any kinetic energy, it will appear for the thermostat as temperature. So, for example, there are simulations we were carrying out some time ago where we're trying to simulate an experiment where they launch a nanotube on a substrate at a very high velocity, like Mach 10, something very, very large. I think it's Mach 7. And yeah, Mach 7. So they launch a nanotube on a substrate at very high velocity, and it's in a vacuum. So what we see is that if we put the thermostat on this nanotube that's moving very fast, it's a translational kinetic energy. It's not really temperature, but for the thermostat, it will appear to be kinetic energy. So we launch it very quickly. It won't even collide with the substrate. So what I was trying to avoid in the simulation is for the thermostat to be removing this translational energy of the nanotube and the nanoribbon and stopping the movement too quickly. So I think one better way to do that I didn't do would be to just, for example, put in the substrate, in maybe at the edges of the spiral, some region that has a thermostat. So the energy has to diffuse for the material, and it will be dissipated in a region that could be representing the interaction with a larger amount of graphene, for example. But so this can be done, but this was not carried out in this particular calculation.
So in that case, the energy is just chaotically bouncing around between one kind of energy and the other, right?
Yes, because the energy has to go somewhere since the energy is constant. So you can see that it really becomes it starts moving around very, very quickly. So this internal motion, you can see that as kind of a higher temperature, right? So in this case here, you have a very high, a lot of motion of the atoms that are inside this graphene here.
Okay, very nice, very nice. So Diane has another question. Go ahead, Diane.
No, sorry, I don't have. I just didn't find out to roll down my hand here. George, I think you're moved.
Sorry, my microphone is. If there are no other questions, we should thank the speaker again. Thank you very much. Very nice talk. It will make for a very nice addition to our YouTube channel. I'm sure the students are going to be checking it out. So Edson is there. Edson, you have any questions?
No, I'm fine. Thank you very much. I just want to thank the speaker. It's a very nice talk. I couldn't. I need to leave by the end of the talk. I have something to do, so I apologize for that. But it was a great talk. Thank you very much.
I was telling Leonardo that it's going to be a very nice addition to our YouTube channel. And I'm going to be asking for the slides very soon, maybe right after the talk. So thank you very much, and thank you for the suggestions of speakers. I'm going to talk to Tommaso and to Rodrigo and see if they would be willing to talk to us.
Okay.
Okay, so we are done. I hope you keep your productivity up. It seems that you are a very productive guy, and you can come next semester and talk to us again.
Yes, that would be nice.
That would be nice. Yeah. Thank you so much.
Thank you.
Thank you. Okay. Bye. Nice.
Okay, thank you for coming.
Okay.
So let me finish.